Welcome, everyone, to day 4 of the Fall 2021 Martin Gardner Celebration of Mind talk series. We are very privileged to have Doris Schattschneider speaking. And Doris is Professor Emerita from Moravian College. In the gathering for Gardner community, she's probably best known for her work on tessellations, tilings. In particular, she is the one who recognized and validated and popularized Marjorie Rice's new Pentagon tilings that she found in response to Martin Gardner's article on Pentagon tilings. But today she's going to be talking to us about some cool stuff from John Conway.
Hi, everybody, and I'm glad to say happy birthday, Martin. It is Martin's birthday today, and so this is a good omen. So what does the Conway Circle theorem say? Well, you're given any triangle, ABC, doesn't matter its size or shape, other than it's a triangle, and you're going to extend each of its sides through its vertices, through its angles. So you're going to, for example, extend side A and side C through angle B, and the amount of the extension is equal to the length of the opposite side. And you do the same thing for extending the other sides through the other two angles. So there we have the extensions. And then the beautiful thing about this, that the circle theorem says, is that if you look at the endpoints of those extended lines, that they all lie on a single circle. So you see the screen, the what's more is that not only is there a circle that joins those endpoints, but the center of that circle is also the center of the in circle of the triangle. So it's a rather amazing and lovely result. And so I want to present a proof that, as I said before, I think most any high school geometry student could produce. So how do we begin? Well, go back to just the triangle and its extensions. And we're going to join those endpoints with lines to create a hexagon. And of course, that hexagon can be any shape depending on the shape of the triangle. What we're going to do is show that opposite angles of the 6 quadrilaterals formed by any 4 of these points on this hexagon in cyclic order are supplementary, and hence each of the quadrilaterals is concyclic, and then necessarily all 6 points will lie in the same circle. So those 6 quadrilaterals, here's one, and its endpoint here is S, so we have SRQP, and then here's the second one where the first endpoint is R, here's the next one, here's the next one, the next one, and the next one. So those are the 6 quadrilaterals that join 4 consecutive points or concyclic points around. We're going to show those points are concyclic. So how do we do that? Well, first look at these 2 triangles that I've shaded, and notice that each of these 2 triangles is isosceles. These are the same length, C, and these are the same length, one red, one green, one red, one green, and they also share the same angle. These are vertical angles. So those 2 shaded triangles are similar, and similar triangles have to have the same base angles. So I'm going to label those gamma. And then we go to the pink triangles. Those are also similar for the same reasons. We label the base angles beta, and these 2 triangles are also similar and therefore have the same base angles, which we label alpha. And so now we've actually labeled all of the interior angles of this hexagon. And as we go around, notice we've got 2 alpha, 2 beta, 2 gamma, 2 alpha, 2 beta, 2 gamma. So 4 alpha plus beta plus gamma has to equal 720 degrees, because that's the sum of the interior angles of any hexagon. And so dividing by 4, we get alpha plus beta plus gamma has to be 180. But now look at this first quadrilateral again, SRQP. Notice that this angle is beta plus gamma, and its opposite angle is alpha, so those angles are supplementary. And similarly, look at this angle, it's alpha plus beta, and its opposite angle is gamma, so those angles are supplementary. Therefore, this quadrilateral PQRS is concyclic. That is, its four vertices lie on a circle. But that same argument will work for every one of the quadrilaterals that I showed you before. And since 3 points that are non-collinear determine a circle, and 3 points here, SQR and RSQ, are on the circle that surrounds this first quadrilateral, but RSQ is also part of the second quadrilateral from RQPV, though the circles that surround each of these concyclic quadrilaterals all have to be a single circle. And so we've got a single circle that surrounds this quadrilateral, but it is the same circle that surrounds all of the other quadrilaterals. So that's your Conway circle. What about the second part of the theorem? How do we show that the center of this circle is also the center of the incircle? Well, remember how you find the center of any circle? All you have to do is draw 2 chords and take the perpendicular bisector of those chords, and where they intersect is going to be the center of the circle. So we're going to take the perpendicular bisector of PQ and the perpendicular bisector of RS. Where they intersect must be the center of this Conway circle. But the perpendicular bisector of PQ is also the angle bisector of angle C, because this is an isosceles triangle. And the perpendicular bisector of RS is also the angle bisector of angle A, because again, this is an isosceles triangle. And we know that the angle bisectors of any triangle intersect at the center of the incircle. So there you have it. That's the whole proof. There are other proofs of Conway circle theorem. You can look some up on the web, but some are also on Colin Mulcahy's webpage dedicated to John Conway. The Conway Criterion actually begins with Martin Gardner's writing. In August 1975, Martin wrote a column on Polyominos, and one of the topics was tiling by Polyominos. And in that column, he mentioned that Conway was checking how many of the 108 heptominos, that is 7 stuck together squares, can tile. And he found a useful test that was sufficient condition for a shape, not necessarily a polyomino, to tile the plane. And in fact, to tile the plane with only 180-degree rotations. The month before this column on Polyominos, Gardner had written a column on tiling the plane with polygons. And one of the polygons was a hexagon, and it turns out that there were 3 classes of hexagons that tile the plane, and the type 1 hexagon was the one that Gardner felt Conway had probably derived this Conway criterion from. So there's a direct link to Gardner with this story of the Conway criterion. So let's begin with Polyominos. These are just, as I said before, stuck together squares, and there's only one monomino, 1 square, 1 domino, 2 squares, 2 trominos, 3 squares, 5 tetrominos, and 12 pentominos. You keep going up and up and up. There are 35 hexominos and 108 heptominos. So here's one of them. Kind of looks like a little horse or something. Well, this one tiled the plane. Well, Conway discovered a criterion that says yes for this tile, and this is what Gardner mentioned in his column. In fact, this little heptomino will fill the plane using only half turns, that is 180-degree rotations. And there's a picture of the tiling. And of course, when you tile by 180-degree turns, every time you turn something 180 degrees, it's upside down. And so notice that half of the tiles are right side up and half are upside down. I mentioned before the type 1 hexagon that was in Gardner's column of July 75. And notice that this type 1 hexagon has two parallel and congruent edges. And then the other 4 edges can be any length or direction you wish. And here's what the tiling looks like. And the congruent and parallel edges just stack up. So they tile by translation. And the other edges are, you turn around 180-degree rotation. But here's how that works. Here's a copy of that tile. And if you turn it 180 degrees about this edge, here's its copy. And then notice that we have a column here of stacked hexagons. What if you turn it around this edge? Well, there's another column of stacked hexagons, and so on. You can turn it around this edge, and here you have a column of stacked edges. And you can turn it around this edge, and you've got the same stacking. So it doesn't matter which edge you turn around, the midpoint of the edge, you create a double tile, and the double tile will just slide or translate to fill the plane. Conway's hexagon tile is just a generalization of this. Replace those straight edges with any other edge you wish, but they have to be congruent and parallel. And replace these other straight edges with centrosymmetric edges, or S-curves. That is, edges that if you turn them 180 degrees about the midpoint, they land on themselves. And this tile tiles in exactly the same way that I showed for the hexagon. You can also remove one of the edges, and then you get what we call a Conway Pentagon tile. That is, there's just one rather than two centrosymmetric segment here. It tiles in exactly the same way as the hexagon tile. And you can do the same to the other side. So you have two congruent and parallel edges joined by two centrosymmetric curves. You can also completely remove these congruent and parallel edges, and then you just have a generalization of a quadrilateral. You have 4 centrosymmetric edges, and you can remove still one of those edges and just have a Conway triangle tile. 3 centrosymmetric edges. So let's go back to the Polyominos. It turns out that all of these, the monominos, domino, trominos, tetrominos, and pentominos, all of these are Conway tiles. You can assign vertices so that each one of these falls into one of those types of Conway tiles. It turns out that of the 35 hexominos, all of these tile the plane, and Conway showed that of the 108 heptominos, well, let's look at this for a moment. Look back at this little guy. Here's 2 congruent and parallel edges, and this one is joined to this one by a single centrosymmetric segment, and then we have 2 centrosymmetric segments that adjoin the edges on this. And so, as you saw before, this tiles the plane. And Conway showed that actually 101 of the 108 Heptomenos satisfies his criterion. And now I wanted to show you what the criterion was according to Gardner. So this is Gardner's description in that August 1975 column. So we examine a tile to see if its perimeter can be divided into 6 parts, A, B, C, D, E, F, and they have to satisfy 2 conditions. There have to be 2 opposite and parallel edges, A and D. That is, they're congruent in the same orientation. And then each of the other 4 edges, B, C, E, and F, have to be centrosymmetric. And any of the 6 edges may be empty, but of course you have to have at least 3 edges to form a closed tile. Well, in 1979, I was writing an article about the Conway Criterion. I thought it would be nice to, since I hadn't seen a proof of it, to write about it and also to provide a proof. And at that time, I attended a special celebration in honor of Donald Coxeter in Toronto. And John Conway was there, and so was Jeffrey Shepard. And I was sharing with John the fact that I was writing up about his criterion, but I also shared that according to Gardner's condition, I could actually find a counterexample. So here's the counterexample. You can see that A and D are parallel and congruent, and the other 4 sides that join them, B, C, E, and F, are centrosymmetric, but you can also see that that's not going to tile the plane. It's going to overlap rather badly. And Jeffrey Shepard looked at this and remarked, "But that's not fair." And I couldn't help but laugh because I'd never heard of a counterexample being told not fair. But John agreed that there had to be a better way to give the criterion so that it would rule out this kind of a counterexample. So this is the Conway criterion that I came up with. So you could have a tile paving the plane by half turns. Now we're going to concentrate not on edges, but on vertices. You have 6 consecutive points, at least 3 distinct on the boundary, consecutive in the sense of traveling a cycle around the boundary, that have to satisfy that the edge V1, V2 is congruent to the edge V5, V4 by a translation that takes V1 to V5 and takes V2 to V4. And the other edges formed by 2 consecutive vertices have to be centrosymmetric. And then the conclusion is that the VI are vertices of a tiling by T that's generated by half turns about the midpoints of the S curves and perhaps by some of the VI. And so why is this sufficient to guarantee that a shape will tile the plane using only half turns? And the first thing you have to ask is what shapes will tile the plane using only translations? And here's a very simple answer. Surely any square or any regular hexagon tiles the plane using only translations. All you do is slide or match the opposite sides by translation. And you can generalize that very quickly to a parallelogram that has opposite sides matching, or what we call a par hexagon that has 3 pairs of matching sides. And if you replace those edges by any shape at all, you still have a shape that has either 2 pairs of opposite sides matching or 3 pairs of opposite sides matching, and they fill the plane just using translations that match those opposite edges. It turns out that only these 2 types of tiles can fill the plane using just translations. So any tile with 3 S curves as edges can be rotated 180 degrees about a midpoint of one edge, and that produces a generalized parallelogram. We know that happens with any triangle, but if you replace those with S-curves, you get the same thing. Notice here the top and the bottom match, and the left and the right match. And if you have 4 S-curves as edges, you do the same thing. Here, if you have a convex quadrilateral and you turn it 180 degrees around one edge, you get a parallelogram. And if you take perhaps another quadrilateral, either convex or non-convex, you might get a par hexagon, that is 3 opposite matching edges, 3 pairs of. And here's a more general tile with 4 S-curve edges or centrosymmetric curve edges. If you rotate that around the midpoint of any one of those edges, you get a new double tile. But notice that here you have this edge matching the opposite edge, this edge matching the opposite edge, and this edge matching the opposite edge. So you have a generalized par hexagon. If you have 2 parallel and congruent curves and you rotate them 180 degrees about any point, they remain congruent and parallel, but they're going to be upside down. And then you can join those to create a tile. And if you join them by S-curves, either 4 S-curves, 2 on each side, or 3 S-curves, 2 on one side and 1 on the other side, or just 2 S-curves, then you're going to see that they tile the plane. Why? Because when you rotate about one of these S-curves, you create a double tile, and you're going to have opposite edges matching. So these are then par hexagons, and in this case, this particular tile creates a generalized parallelogram. And we know that these generalized par hexagons or parallelograms tile the plane. But we know they tile by translation. So I claim that the Conway tiles fill the plane using only half turns. So why is that true? Well, another fact, if you rotate a curve 180 degrees about a point and then rotate that curve 180 degrees about another point, the final image is congruent and parallel to the original. In other words, mathematically, the composition of 2 half turns is a translation, and the vector of the translation is exactly twice the vector created by going from the first half turn center to the second half turn center. So that implies that a Conway tile needs only half turns to fill the plane, because the combination of 2 half turns will produce the needed translations. So here is the first half turn, and we get the generalized parallelogram. And then if we now rotate about the second half turn, this tile lands up here, and you see it's the translated image of the original tile. And you can do this if you have a tile that has just one centrosymmetric curve joining the 2 parallel curves. If you rotate first about this half turn, you get your generalized parallelogram, but then now you're going to rotate about a vertex of the original tile, and there's your translation. So all you need is half turns to have any Conway tile fill the plane. And there was some really wonderful results of the Conway Criterion that are written about by Jin Akiyama and Kyoko Matsunaga that appears in the Mathematical Intelligencer issue that is dedicated to Conway. And I wanted to point these out because I don't know if they've been pointed out elsewhere, but in the abstract for the article, Akiyama and Matsunaga say we highlight how playful the Conway Criterion is in the fields of tiling, folding, and Dieudonné transformations. So one of their results is every Conway tile is foldable into either an isotetrahedron, that is a tetrahedron that has congruent faces, or a rectangle dihedron, that is a rectangle where it's basically a double rectangle where the edges are pasted together. And conversely, every net of an isotetrahedron or rectangle dihedron is a Conway tile. And then a second very surprising result is that superposition of two tilings by Conway tiles having the same area can produce what's called a Dieudonné transformation of one tile into the other. And those of you who don't know what a Dieudonné transformation is, Dieudonné first wrote about how you can transform an equilateral triangle into a square. These have to have the same area to begin with, by cutting up, dissecting the one, and in a way that you can actually hinge the pieces together and then rearrange them, and they fold into a square. And this is the superposition that Akiyama and Matsunaga show. If you have your triangle and you make it have 4 vertices, the 4th vertex is the midpoint of the base here, then of course you have 4 straight lines, so you have a Conway triangle of 4 S-curves. And similarly, you can divide up the square into a Conway tile. Here you have one very short edge matching by translation this very short edge. And of course, then there are 4 other straight edges, which are also centrosymmetric. And if you take the midpoints of all of those centrosymmetric edges and they line up as I've shown here, then the red lines that come from the squares divide up the equilateral triangle exactly into the dissection you want, so that when you turn it, you get the square. In other words, here's the blue lines give you the dissection of the square. So I found this absolutely amazing, and a result of the Conway Criterion that I'm not sure that John himself knew about. During the pandemic, I participated in a project to produce an app called Conway's Magical Pen. Anton Baker, who is a sculptor and had an exhibit, first virtual and then in person, at the Museum of Mathematics in New York, was the sponsor of this event. And the developers were Herman Tulliken and Jonathan Bailey. They were in Chile, and I here in Pennsylvania was the math consultant. We wanted to create an app that you could literally freehand create Conway tiles, and then of course they would tile the plane. So this is a web-based app. There's the link for it, www.conways without the apostrophe magicalpen.com. And I want to show you a couple of results from that. So these are 2 videos that will show you how it works. So you click on the Start Drawing, and then this menu comes up. Here I've chosen, I want 4 connected S-curves, and then you just draw the first curve, and this is going to be an S-curve, a centrosymmetric curve. I only draw half, and the other half gets automatically drawn. Here's the second S-curve, and here's the third S-curve, and the 4th S-curve. I only draw half, the other half comes automatically. And then you can play with the edges of the tile to change them as you wish. And then you can say, show me the tiling. And then you can change colors. I think you can see what we're getting here. This would be my Christmas wallpaper or wrapping paper. You can change the color of the outlines of the tiles. You can also change the thickness of the outlines, and you can also scale. And here's the second one. Here I'm going to draw with two parallel curves connected by two S curves. So here's the first curve. You just draw one and the parallel and congruent one comes free. You can then move them so that they're in relation to each other however you wish. I'm going to try to make kind of a vase or a jar. So there's my S curve. And here's the second S curve. And then you can again adjust by playing with the edges so you get what you want, or at least close to what you want. And then show me the tiling. And again, change colors to whatever you want. Again, I'm going to change the outline to black. And I definitely want to zoom so I can see much more of the whole tiling. I wanted to show you this. This is one that was done by a 10-year-old. This is just 3 S curves. Kind of looks like perhaps greyhounds. And this is just a fanciful one that has 2 matching curves, free-form curves. There they are. And here's one S curve and a second S curve joining. And this is just one S curve here. So this is just a fun one. And so that's my presentation on the Conway Criterion. And I hope that you can find it on the web and enjoy making some of your own tessellations with Conway tiles.
Thank you very much, Doris. That was both beautiful and exceptionally clear. And I think all of us can learn a lot from your presentation skills. So thank you. And I learned a lot of new things, and I'm going to have fun playing with that app. So I see we've got a ton of comments in the chat, mostly congratulations on how wonderful a presentation that was. Let's see if there's any questions. Is there a converse to the Conway Criterion?
Actually, I'll say not that I know of. Both Marjorie Seneschal and I spent many hours trying to prove prove the opposite. That is, if a tile can fill the plane using only half turns, must it be a Conway tile? And if it creates an isohedral tiling, the answer is yes. The Conway tiles are exactly the 5 fundamental regions for P2 tilings, but there might be some kind of a non-isohedral tiling that is created just by somehow keep flipping a tile, and it's not. So we did not succeed in proving that. It would be wonderful if someone could prove it. So that's a great question.
Simon Allen asks, you put up the slide where you had the equilateral triangle to a square. I tried to screen grab it, but missed it. You probably want the overlap, but for those who haven't seen it, this is Dudonet's actual inch dissection of a square to a triangle. Most of us have probably seen this, and probably what Simon is asking about is the overlap. Are all 35 hexamonos Conway tiles?
I'm sorry, I should have written down whether, I think the answer is yes. I know they all tile, but I can't for sure say that they're all Conway tiles, but they all do tile. It's possible that one or two of them needs a reflection.
Dan Bach says yes, and Wikipedia says yes to that question.
Okay, thank you. Thank you for looking for it.
I wonder if there's a tile that tessellates with only 180-degree rotation. So some of the tiles are upside down and others are right side up, but the proportion is not 50-50.
It's possible that some of these tiles, and the Polyominos in particular, will tile in other ways than the way that I showed. So I suppose that's possible, but I would think that you would need to have a clump of more than two that's doing the tiling in order to create that asymmetry, if you wish. That would be my guess. But many of the Conway tiles, if they have the right shape, and as you can see that they can have an incredible number of strange shapes, they don't necessarily have to tile using the 180-degree rotations where through the midpoints of the centrosymmetric segments. If they're the right shape, there might be other actions or translations that are not created just by those half turns. But my guess is you would want to have some kind of a clump to give the asymmetry.
Oh yes, can you please show us the heaven and hell ball up close?
Oh, it's a reproduction. It's certainly not Escher's, but it was. Here it is. Yeah.
Fabulous.
This was made by the Escher Foundation, or the MC Escher Company in Barn. It was probably made around the time of the centennial for Escher's birth, which was 1998. That was the centennial. So that's what it is.
Beautiful. So thank you again, Doris, for that absolutely fabulous talk. That was a real treat. And I'm sure everybody here really enjoyed it.